We are going to discuss current electricity today, most important chapter. So first what we are going to do is that we are going to see what are the subtopics we have got in current electricity, and like what are the things we need to learn in this chapter before going to solve questions, right? Very important chapter, no doubt. Weightage wise, very high weightage. Actually, this is the highest weightage chapter. So like when you are solving question from current electricity, you need to know certain things very clearly. Okay, what are the things that we have to know is first part. Actually, first part is completely like what you say theory things are there. Like you have to know about drift velocity. That is one important area, drift velocity. Okay, drift velocity, and you have to know the current in terms of drift velocity. The formula of current, so like electric current in terms of drift velocity, current in terms of drift velocity, right? Drift velocity is very important thing, and formula of drift velocity you have to know. Actually drift velocity will get Vd is equal to small e capital E divided by m into tau. From here you will get the formula of conductivity, resistivity, and all those. That sigma formula is important. Okay, rho formula is important. Those things are important area, first part. And here also you get something called mobility. 2020 question was there. Just they have asked mobility, that is drift velocity by electric field. So this part actually is very much theory part. Much is not there, but important. Last year also we have a question, before also we have a question. So like consistently they are concentrating. Second part is like you have learned already in 10th class, Ohm's law concept. Ohm's law concept here, and the most important like resistivity and resistance relation. That is, you know, rho equal to you get RA by L, right? But concept is very simple, but numericals can be many in this. Like when wire is stretched, what happens to the resistance? Like wire is stretched, the resistance is not proportional to L, it is proportional to L square. So like R1 by R2 is equal to L1 square by L2 square is equal to, you have got A2 square by A1 square is equal to radius to the power 4 by radius to the power 4. Actually this is very important. Wire is stretched means resistance will get affected, resistivity will not get affected. Okay, so there are two different situations we have. Two different situation means one wire is actually just you are cutting the wire. When you are cutting the wire, resistance is directly proportional to length in that condition. So cutting the wire is a different situation. Cutting the wire, when you are cutting the wires, no problem. Cutting the wire means resistance is directly proportional to length, and this situation is applicable when we are stretching the wire. So when you are stretching the wire, then you can apply this, stretching the wire. So when you are stretching the wire, why we are getting like this? The reason is volume remains constant while stretching the wire. Okay, volume remains constant means you will say that A1 L1 should be equal to A2 L2, right? So anyhow, this is the most important part, rho equal to RA by L. And you know that resistance depends on length, resistance depends on area, but resistivity, this is your resistivity only depends on temperature, okay, and nature of material. So these are the first part when we actually can get questions from these two areas, right? So these two areas are very important. First is like very conceptual thing, right? Second thing is Ohm's law. In that, resistance relation with length and area of cross section important, and that relation will actually change when you are going to stretch the wire, right? So that is important thing. Then another important thing you have in this chapter is, this is the first part of the chapter, very important. You get usually a question from here. Every year you get a question from this part, so it should not be neglected. So resistance, now actually when we talk about resistance, here you have to find out effective resistance. So effective resistance finding is like not so easy, because here you will have many different situations. So we have to actually find effective resistance. effective resistance in different combination. Effective resistance in different combination, it means you will have different kind of circuit diagram. Okay, effective resistance in different condition. This is one important area. To be frank, directly they are not asking question on this, but capacitor they are asking this series parallel connection, but this knowledge is very important. Until and unless you don't have this knowledge, you cannot solve question in electricity, right? Next we have got like effective resistance in different condition means, I mean to say series and parallel connection. Series and parallel connection actually very simple concept, but when it comes complex circuit sometimes it actually gets little difficult. Now you will have here like you will actually study about simple diagram, simple circuit diagram, like simple circuit diagram question you have to like two batteries are connected kind of thing, and with that some resistance is connected, right? Like this kind of situation. So very simple kind of situation. Then you need to know like how to find out current and all that, how to divide the voltage, how to find out terminal EMF. So actually certain things. What is that? You need to learn series connection of cells. Here you are learning series and parallel connection of resistance. Here you are learning series and parallel connection. Series and parallel connection of resistance you are learning. Okay, but here series connection of battery, very important, very important series connection of batteries, because what happens in some situation you have been given two batteries, right? They are connected in series connection. So two batteries connected in series connection means how to find out effective EMF, how to find effective voltage, that becomes very important. Not that, you have to find out even parallel connection of batteries. Parallel connection of batteries, right? So when you take parallel connection of battery, that time also how to find effective EMF. So four part I have told you, like first part drift velocity, current in terms of drift velocity, and drift velocity is actually small e capital E m tau. From here that part, then we have discussed about resistance and resistivity part, important, very important. The third thing I told, like we have to go for effective resistance in different condition, and particularly you should be very have perfect understanding on this series and parallel connection. Series and parallel connection actually is very important. The reason is, unless you know series and parallel connection, if you don't know, you actually cannot solve questions, not possible practically to solve, right? So that thing becomes very important for you here. Okay, so actually I told this parallel connections and series connection of resistance as well as batteries, very important. The next we have another 3 or 4 things you can tell. Okay, one very important thing is like you have to know how to calculate the EMF, like calculating EMF, not like EMF and terminal voltage difference you have to know, right? So the other things we have to know EMF and terminal voltage. What actually the difference between them? So EMF and terminal voltage formulas are less here, but the thing is that questions will trouble you sometimes, and NCERT book back question is also there. EMF, terminal voltage. Actually, what is terminal voltage means what is effective voltage which is given to the external resistance. EMF means what they are showing you, like when you go and get something like 10 volt is written on the battery, let us say, but that 10 volt is not actually what we are utilizing. We get less than that, and what we get is nothing but your terminal voltage, and the relation actually will be like V equal to E minus IR. Okay, E is your EMF, actually E is your EMF, and I is the current, and small r is the internal resistance. V is your called terminal voltage, like like what you say, if you take a battery, let us say, and you have actually connected some bulb. So bulb generally like we can represent anyway, but here what we do is that we are going to just have a resistance. Okay. And what actually you have been given is EMF, like this is a 10 volt battery I have purchased and all that. Okay, you have purchased 10 volt battery, that is fine. But that 10 volt is not going to be utilized by this your external resistance. What will happen, whatever voltage you are giving, actually you know that current flows from positive to negative terminal, fine. So current will go from positive to negative terminal, that actually in the external circuit, right? Inside the battery, current actually flows from negative terminal to positive terminal. Outside the battery, current goes from positive to negative. But inside the battery, current goes from negative to positive terminal, and actually that battery also has got some resistance, and that is known as internal resistance, right? But that there is some voltage is given across the internal resistance, voltage drop is there across internal resistance, but that makes no sense for us. Okay, so that is not important for us. So here what we are going to do is, we are here going to actually see that things. What is important for us? For us, important is only that external voltage is important for us, right? So external voltage, how do we write, is actually we will be writing like this way. So whatever you are taking voltage, right, that is for this resistance. This is your EMF, and actually whatever the voltage it is getting is V, and this V is important for us, not like that, and nothing like that, nothing is important other than that. V equal to, actually you write E minus IR, right, fine. V equal to E minus IR, V is called terminal voltage, E is actually EMF, and I told it is small r your internal resistance. So here actually total current, whatever it is there, total current is passes through internal resistance also, inside the battery also it passes, right, inside the battery also it passes. So total whatever voltage is there, you can say that external voltage is I into capital R, and internal voltage I into small r, that is not voltage, that is total EMF. EMF is divided across external resistance I into capital R, I into small r, right. So this I into capital R actually you can write as V, then V plus I into small r, actually nothing but E, that is what EMF. That's what terminal voltage you get, V equal to that EMF minus I into R. Remember that when you are calculating current in this condition, for calculating current you are using EMF, because here from this equation you can see that current actually you get I is equal to E upon small r plus capital R, right. So current actually you get E capital R plus small r, that is current, and this is your terminal voltage, and this actually is valid when battery is discharging. When battery is discharging, right. So one important area from where question actually will be asked, not every year we can say, but like this is the area where you get actually confused. So the same formula will change when battery is charging. So when battery is charging, the terminal voltage formula changes, it becomes V equal to E plus I into small r. So this is the thing you write when battery is charging. Battery is charging, like your mobile phone gets switch off, and like you connect with the external supply of current, I mean you have something, okay, which you connect and you again charge the battery. So this time this formula V equal to E plus IR, we will write battery is charging in that condition. Battery is charging in that condition, we have this one. Battery is discharging means when you are using the battery to light the bulb or whatever, you are just using the battery, you are consuming the energy from the battery and you are actually giving the energy to the battery, right. So next one, here we can say another thing, we can say that V can be equal to EL. So in what condition? Best thing, don't use the battery. If you don't use the battery, what is zero? Current will be zero. Current is 0 means in that condition anyhow current is 0 means V will become E. It means internal resistance is not effective. Internal resistance is not effective in this condition. When you are not using the battery, your internal resistance is not effective. So that V and E both becomes equal. So that is the third condition. Why I have explained you, because this is the area, small thing of this chapter, but confusion will be more. So that I thought let me focus little on this, right? Next, that is terminal voltage and EMF, very important, okay, because sometimes it troubles. Next, the important area which you have is actually in this is Kirchhoff's law. Famous topic, all of you will be knowing Kirchhoff's law because you will be learning 12th class. Kirchhoff's law, and see here you are not going to solve very difficult question and all that, very basic question they ask you, and I hope you all know the first law is so easy, okay, first law will be so easy, that is not a problem, okay, problem only with the second law will be asked mostly, first law will be very simple, okay, first law is not a problem. So you have Kirchhoff's law, first law is there, so first law questions are less but very simple, that is conservation of charge, and you have got second law, question will be asked on second law mostly, and second law can be very complicated at the same time, but we are not interested, we may be interested for some student, but they are not interested, Neet, NTA is not interested to ask you very difficult questions, so my suggestions never go to very difficult questions, okay, second law actually will be simple, okay, second law it is actually based on energy, for second law is based on energy conservation, based on energy conservation, and first law is based on charge conservation. Okay, so Kirchhoff's law, why? What is the necessity? Kirchhoff's law actually solve questions complex, like when let's say you have connected one battery, then one resistance, again you have connected another battery, then resistance, like that, again another resistance, again battery, kind of thing is there, and you are like, sir, I know the potential at this point what is there, and I need to know the potential at this point after the current is going either of direction, you can say. So in that condition we can actually use Kirchhoff's law directly, very simple. Some we have sign convention for Kirchhoff's law, that is actually important, and I think I will discuss that because that is makes confusion to the students. So Kirchhoff's second law actually is important, question based on Kirchhoff's law is important, right? So here actually we can apply, how to apply sign convention, that I will discuss with you because that makes confusion to the students, okay. So like sign convention, when you are applying sign convention, so we are going to see the sign convention in Kirchhoff's second law. Actually when you take a circuit, in this chapter we only take battery, then resistance, okay, then you can take another battery, we don't have any inductor, we don't have any capacitor, nothing. So actually in this chapter we are actually supplying DC voltage, and lot of batteries are there, lot of resistance can be there, internal resistance can be there, that is not a problem, okay. Only thing is that you could have more than one battery, more than one resistors to be connected, like, so let's say this is having EMF E1, this is having EMF E2, this is having EMF E3, and this is having EMF E4, right. Let's say that resistance for inch of the battery can have internal resistance too. So R1, this is R2, let's say internal resistance of this is R3 and this is R4, like, so like we need to find out current. I have taken very basic question on this, like we can name it, like let's say this is A, this is B, this is C, and let's say this is D, right. So actually generally if you have been given a closed path, you can actually, you have to find out current means take the whole closed path. Generally they are not asking question, they will ask between A to D, means that also I will tell you how to find out. But here if you have to find out current, they tell you find current, right? So how to find out current in this? You take one direction of current, any direction you can select, because we don't know the correct direction of current, so one direction you select. Okay, you get an equation here, you get an equation. After solving the equation, if current is coming positive, whatever direction you have taken, that is perfect. But if you are getting negative, it means the direction of current what you have taken is wrong. Wrong in the sense you have taken reverse direction. But I am more interested right now in actually to tell you sign convention. How to apply sign convention. So in this closed path, when you are going across the battery, so situation number 1, when you are going across the battery, you can have two things. Either you can go from positive to negative terminal, otherwise you can actually go from negative to positive. These are the only two situations come across the battery. When you go across the battery, what happens? Either you have to go from positive to negative terminal, or else you have to go from negative to positive. Any one of the situation, fine. And the first one, what happens actually when you are going from positive to negative terminal, your EMF of the battery is taken as negative. The reason is you are losing the potential. You are going from higher to lower potential, so you are losing the potential. So actually EMF of the battery will be taken as negative. So when you are writing, let's say battery 5 volt is given, so you write minus 5V, you will not take plus sign. And now in the second condition, actually you are going from negative to positive terminal of the battery. So in this condition, actually you are gaining the voltage. So that EMF will be taken as positive. Okay, so this is like two different sign convention for EMF of the battery. It can be negative, it can be positive. Positive in one which condition, when you are going from negative to positive terminal, and when we are going from positive to negative terminal. Now let's say third condition. Third condition, what is there means, here actually you again will meet resistor. When you are going in this closed circuit, you will meet resistor. Let's say this is a current and this is resistance R. So when you are going in the direction of current, let's say this is the point A and this is the point B. So when you are going in the direction of current, so you know that when you are going in the direction of current, the point A will have more potential, because the reason is simple. Okay, the reason is simple is why, because this point A will have more potential, this resistance will eat some of the potential. Eat in the sense you have to drop some voltage to him, because resistance will come, current is going, resistance will definitely take some kind of voltage drop. So when the voltage drop comes here, so ultimately that becomes less. So definitely you will say, sir, potential at B is less than potential at A. The reason is simple. Some of the voltage you have to give to this resistor. While crossing the resistor, you have to give some kind of voltage to him. So in this condition, it means IR is negative, because you are losing the potential. So IR actually becomes negative. The last condition in this is when again you are going through resistor, right? So this is current, same thing, resistance is R. Now you are going opposite to the direction of current. So when you are opposite to the direction of current is there, same situation is there. This is B and this is A. So actually you are finally going from B to A. So ultimately you are going from low potential to high potential. So here for this condition you will write IR is positive, right? So these are the four important sign convention of Kirchhoff's law. First one I have given you. When you are going across the battery from positive to negative terminal, you are losing the EMF. EMF of the battery is negative. Second one I have given, when you are going from negative to positive terminal, you are actually gaining the voltage. So like EMF of the battery is taken as positive. Third condition, when you are going in the direction of current, okay. So you know that when you are going across the resistor, some voltage is dropped, so your voltage is decreasing. So here IR is negative, right? and the final one we have taken is when you are going from A to B in this condition, actually A is having more potential, B having less potential. So this is IR is positive. I hope it will make some sense for you. Okay, you will maybe able to understand sign convention, right? So this sign convention we are going to use for the same diagram here. Okay, because we have to know why we have learned this sign convention. What is the necessity of this? So let's apply this sign convention for this whatever we have drawn the diagram, right? So for that diagram we are going to learn the sign we are going to write the equation using our sign convention whatever we have taken, right? Now let's say that, as I told, like we don't know what is the direction of current, right? We don't know direction of current. Take one specified direction. Let's say this is current I, and we will just write the equation here, general equation we will write using Kirchhoff's law. And if you take the circuit, closed circuit you take here, like you are starting from A, you have to come back to A. So like you will take circuit A, B, C, D, A. This is closed circuit, right? You take circuit A, B, C, D, A, right? You are starting from A, you are returning back to A. So here no division of current, so it is a simple one we are writing. So we are starting from A. Okay, we started our journey from A. Okay, we started our journey from A and we are going towards B, right? So we are going towards B in this one. So what actually we do is that, so when we are going from A to B and B to C, then when you are going here, so current is actually I only here. So when you are going in the direction of current, we told that IR should be taken as negative. So you will take minus IR4, right? IR4. Now here this is your positive terminal and this is your negative terminal. So I told, when you are going from positive to negative terminal, EMF of the battery is taken as negative, so minus C4, and the same current I is passing, and this resistance, actually we have internal resistance R4 we have taken, and this resistance something, let's write this is R1, and let's write this is R2, and let's write this is R3. So we are coming from A, again let's start from A to B, nothing is there, B to C, when we are going first we are meeting this external resistance, so in the direction of current you will write minus IR1, okay, then internal resistance of the battery R4, minus IR4, positive to negative we are going of the battery, so minus C4. Now again you are going in the direction of current, again you will write here minus IR2. Next here you are going from negative to positive terminal. Okay, negative to positive terminal and internal resistance I have specified here. So you write that also, minus IR3 plus E3. Why plus E3? Because when you are talking about terminals of the battery, we are going from negative to positive terminal, right? Negative to positive terminal, so EMF is taken as positive. Again you are going from here, from D you are going, again you are going from negative to positive, so again you will write as plus E2, and again you have got some internal resistance, so as usual you will write minus IR2, and next again you are going, means you are getting minus IR3, then plus E1 minus IR1 equal to 0. We have started from A, we return back to A, and we have got a heavy equation. Heavy in the sense, not heavy equation, because only one current is there, I, because in some situation we have to divide the current, but here current is not divided. Just I told you to how to apply sign convention, right? So sign convention you can apply, you can go from A to B, B to C, C to D, and D to E, and you can actually write the equation. One of the year they have asked only to write the equation, not to solve the question. Okay, so you can apply the same method. Next I will tell you 2018 question was there on this, how the question was. Exact number I will not tell, but exact question I will tell you. Numerically it will not be exact, but like conceptually it is exact. Like 2 ampere current is there, like this is 3 ohm resistance. Let's say this is 5 volt battery. Let us say again here 1 ohm, internal resistance is not specified, and very basic question was there, like this is the point A and this is the point B, and they are asking you find the potential difference between A and B. VA minus VB is equal to how much? Like he is interested to know like what is the potential difference between point A and B. So like apply Kirchhoff's law, like very basic question. So you take the potential at A is VA. Like in the direction of current you are going. So when you are going in the direction of current, I told IR take as negative. So current is 2, resistance is 3. So 2 3s are your 6. And again you are going from positive to negative terminal. So you get actually minus 5 volt. Again you are going in the direction of current, means again same current will be there 2 ampere. So you get minus 2 minus VB, that equal to 0. So you can write VA minus VB, potential difference. If your plus minus is very important here. So here 13 volt get. It means the potential of A is greater than potential of B by 13 volt. So this is the answer. Actually that was 9 volt answer. Actually number was different, but this was the question, exactly same model we have been asked, right? So I told you, just because sign convention travels some time to the student. So this is about Kirchhoff's law, right? First law very basic, you can actually understand very easily. Second law, because of sign convention only, it makes little like compared to first law, it is little standard. Okay. So this is about Kirchhoff's law. Then what are the areas we have? Another area is in this chapter is next one. Let us go is we have to know this. What do you say? Heat developed across resistor and power. Actually, heat developed across resistor. We call power concept also. Heat developed across a resistor. Then you have got very important power concept. Generally they are asking question alternate here. Electrical power. Power is not like simple concept, but understanding is very important. Okay, next one here you actually should go through is. Then after that we don't have much of the things. Then left out is your Wheatstone bridge. Wheatstone bridge is there. An application of Wheatstone bridge we have. Okay, application of Wheatstone bridge we could have is your what do you say, you can call this one as meter bridge, because they have deleted this part. They have deleted the part of potentiometer, which was actually very important, and they used to ask a question. So Wheatstone bridge, and from there only application you have got is meter bridge. Right. So actually overall things what I have told, heat developed across resistor. Okay, and here you can actually learn some conceptual question on power. Some conceptual question on power, because which bulb will be brightest, some conceptual questions on power. Like they will give you kind of something and they will ask you like which of the bulb is brightest. So like you should have some clear understanding of this power concept, then you can solve this. He developed, actually you know that in series connection if you have connected to resistor, then better take heat developed formula is equal to I square RT. So like if it is having resistance of R1, it is having resistance of R2. Then heat across the first one you can write I square R1T in series connection. Okay, and S2 definitely you can write I square R2, right? Heat developed across second resistor you can write I square R2 into T, right? Same thing if it is given parallel connection. parallel connection is given to you means, so here in this connection parallel connection is given means actually you can use that heat developed is equal to V square by R. So like let's say this is your R1 and this is your R2. So heat developed you can write for the first resistor in parallel connection V square by R1 into T. For the second one you can write as V square by R2 into T. Like, so that series and parallel connection concepts are important, right? And after that, finally after all these things, what is there means some conceptual things are there which is important, and that is actually fuse wire. They have asked questions, so like fuse wire. Fuse wire is actually one important thing. Fuse wire, actually you know what is the use. It actually prevents high voltage current. High voltage current. It's a safety device, means it actually prevents. I am connected in series connection actually. Fuse wire always connected in series connection. Series connection to the main. Okay. And the property of the fuse wire, actually it should have high resistance. High resistance and low melting point. Okay, one time they have asked this also about fuse wire, right? So this is actually another, other than that, what you know, what you require is some conceptual understanding of voltmeter and ammeter, right? So like you have voltmeter, right? So in ideal voltmeter you have to know what is ideal voltmeter actually is. The ideal voltmeter concept you have to know. Ideal voltmeter means what is the property of ideal voltmeter, that is important. Okay, so that things we have to little concentrate, because on that concept also question was there. So like voltmeter. Ideal voltmeter means ideal voltmeter or voltmeter, whatever you say, should have infinite resistance, but not practically possible. Infinite resistance. What does it mean? Means the meaning is that whenever voltmeter is there, voltmeter always connected in parallel connection, and you connect some resistor in series, it makes no difference. You are finding, let us say you are finding voltage across some resistance. While finding, actually you will find out potential difference from here to here, right? So why it should have infinite resistance? Because when current is passing, like all the current should pass from here only, so that actually you can measure the exact voltage across this resistor, right? And on this concept only question I have asked one time, if you connect some resistance in series with voltmeter, will not affect the resistance of voltmeter. The reason is simple, because voltmeter is having already very high resistance, so it makes no sense to connect some resistance in series with that. So voltmeter is that. If you take ammeter, so ammeter resistance should be actually very low or zero resistance. So this ammeter should have zero resistance. Okay, should have zero resistance, because it is connected in series connection. Ammeter will be connected in series connection, voltmeter will be connected in parallel connection. Should have infinite resistance, should have zero resistance. Some conceptual question you may be asked here, right?